All right, let's talk about simple harmonic motion. Now, you see, um, simple harmonic motion simply means um, when a restoring forces or a restoring force rather always returns a body that is in a motion, in constant motion to a particular position. So, um, or you call it periodic motion. So that there is a force that is causing a body to go back to its initial position per time. That force is causing that body to um, go back to its position per time. So that brings about a simple harmonic motion. Harmonic because it is rhythmic in a sense. So for example, physicists often describe the motion of a body that is attached to a spring. You understand? So if a ball, for example, on an horizontal surface, usually that's the way it's been described in physics by physicists. So if a spring, as it is like this, if an external force is applied on this spring, this body, so so actually the body will continue in motion forever if there are no provided all other conditions being equal. If there are no friction, no according to Newton's law of first law, inertia. So that body will continue in that motion forever. All right. But in this place, what we notice is this. So this is often talk about this with respect to, simple harmonic motion with respect to the motion of this ball in this as attached to this spring. So if I displace this ball, this spring a little, so what you are going to notice is a back and forth motion, so that you see the spring go like this when it and in its during its when it undergoes maximum displacement, and then this is the equilibrium position. This is equilibrium position here. This is the maximum displacement. Then you see it compress, undergoes some compression also. Let's draw the compression well. So you see that body undergo compression and expansions. So this is going to be its minimum displacement and its maximum displacement. And it's going to continue in that motion like that. Do you understand? So it is often, it has been described that the motion of this body in the simple harmonic motion is likened, is in fact equal to is the same in a sense as the motion of the body in a circular path. And I'm going to show us how. So how is the motion of the body in simple harmonic motion? How is it equivalent to the motion of a body in a circular path? Now look at the motion of a body that is going like this in a circular path. Just watch with me. I want you to create the 3D motion in your head. Now, you see, a body that is, although it is not exactly 3D, these 2 dimensions, but I want you to create it in your head, that 2-dimensional motion. So this body is moving like this, while this one is constantly moving like this, right? Now, if I bring this body that is in circular motion, if I were to, now what you are seeing is that circle. If I were to flatten out that circle, so watch me, let's flatten out the circle. As we are going like this, now I'm flattening it, so that after a while, now the circle is now like this. So what do you notice? Now, if you were to observe this, if not for the fact that it is going back and forth, my hand is going back and forth, the only thing you are seeing is a rightward and leftward movement. That is the only thing you are seeing. A rightward and leftward movement. If I slow it down a bit. So what you are seeing is a rightward and leftward movement, which is the same as what? The simple harmonic motion of this body. So that is why a body that is moving in circular path. So let's bring back the circle. So you see now, a body moving in circular path is the same as a body that is moving what? In simple harmonic motion. Mathematically speaking, actually. So I'm going to show us the mathematics, and that is where it basically comes from. That is what I want to bring out. All right. So now we observe that this body is going to have, since it is equal to this, can be related to a body moving in circular motion, we can then say that it has all the properties that this guy is going to have. All right. So, but one thing that is obtainable here is the fact that Hooke's law actually works. That the extension that is produced by this spring is that the force, the extension that is produced is directly proportional to the force, isn't it? But in this case, I would like to use x for my extension. X meaning displacement. All right. The displacement that is produced, the extension that is produced by the spring is directly proportional to the force, provided that what the spring constant is constant, and spring proportionality limit is not exceeded. As you know, it says that the Hooke's law says that the force applied on the spring is proportional to the extension produced, provided that the proportionality limit is not exceeded. So in this case, we are talking about the fact that there is a spring constant here. So, and since the body is always moving against the motion of the spring, so we have K negative sign here, a negative sign here. So, but we are not particular about Hooke's law exactly here. Recall now that there is going to be an energy. That's what we want to actually analyze now. What are going to be the property of the energy stored on this body? Now, there are two types of energy, as we already know. We're going to come back to this circular motion thing. But there are two types of energy that's going to be on this body. We have its potential energy, and because it is moving, it's also going to have what? A kinetic energy. Now, at this region here, is going to be, so when this body moves like this, when the body moves like this, it's going to experience stops or pauses, brief pauses at the point of its maximum displacement. And here, it's going to experience it's going to experience what? A pause also at its minimum displacement. So, because of that, at this point, kinetic energy, Ke, so at this point here, Ke is going to be 0. And at this point here also, Ke what? 0. Why? K is going to be 0 because see, the body is not moving at this point of maximum displacement and this point of minimum displacement. So velocity is going to be what? 0. So since velocity is 0, recall that K is equal to what? Half mv squared. So, and since this is half mv squared and v is 0, so K is going to what? 0. So the same thing here. K is going to be 0 for that same reason. So what does that mean? It means that total energy, but recall that since the body is under influence of force, it's going to have some energy, right? So since it's going to have, and it's moving from distance, so it's going to have some energy. It's going to have energy. So it means that the only energy you are going to find here, let's clean this first. The only energy that will be obtained, that the body will have here is what? Potential energy. So all its energy has been converted to what? Potential energy. So in this case, the potential energy is going to be what? No, now not mgh. Now it's going to be what? Half Ke squared, because that is energy stored in the string. Energy stored in the string, which is basically from half Fe. Right. So that is going to be the potential energy. So at this point, and at this point also, the potential energy is also what? All energy is going to be what? Potential energy. But as it is moving, I want you to observe this now. As it is moving in this direction now, towards this point of equilibrium, as it is moving, the potential energy will be undergoing several conversions to what? To kinetic energy. So that if it started at an energy level of, let's say, 200 joules at this point here, as it is moving towards this point of equilibrium, if the entire total energy in the system is 200 joules, it's going to be undergoing conversions at each stage until it gets to this equilibrium point. So what do you have here? At this point of equilibrium, so what do we have here is that the kinetic energy will be going, the potential energy that we have is going to be converted to kinetic energy little by little as it's undergoing this motion. So as it is going, some of the potential energy would have been lost to kinetic, will become kinetic energy, so that we have maybe, for example, at a point here, at the point on the path, we're going to have 180 joules for potential energy, then 20 joules for kinetic energy. So that is given the fact that total energy must be conserved, conservation of energy. So, and as it's going again, the potential energy might become 120, so that the kinetic energy has become what? 80 joules. And like that, until total energy has been converted to what? To kinetic energy. And where is total energy converted to kinetic energy? Is this point of equilibrium position. Why? Because this is the point of no displacement. So x is 0 here. This is the point of no displacement. So potential energy here, P is going to be 0. Why? Because there's no displacement. But K is going to what? Maximum. God bless you. K is going to what? Maximum. You understand, right? Because in this place, the velocity will be maximum. Because this is the time where the body is set to move. Do you understand? Because here, the body is set in motion. Like that was where it was set in motion from the beginning. So the body is going to have its maximum kinetic energy. So we have half mv squared. So that is going to be the energy there. So, and then I talked about the total energy in the system. So as along the path, the total energy in the system is going to be potential energy plus what? Kinetic energy. So we have half kx squared plus what? Half mv squared. All right. But if, so this is equation 1. So, but if we have that, so no, this is supposed to be equation 3, since this is equation 1, this is equation 2. But if the body is at its maximum displacement, at the point of maximum displacement, it means that the total energy is going to be what? Only half kx squared. And if it has its equilibrium position, the total energy is going to be what? Half mv squared. That's one thing I want to specialize. And notice that it is at this point, since K is maximum here, total energy is still conserved. If we are starting at 200 joules, that body will still have what? 200 joules of energy. And what that means is that at every particular instant, therefore, in the entire system, therefore, total kinetic energy is always equal to what? Total potential energy. Is that okay? So that half K squared, half kx squared will equal to what? Half mv squared. So this cancels this. Then we have kx squared is equal to half mv squared. Then we can find the velocity of the body. So what is that velocity with which that body is moving? So v squared is going to what? Kx squared over m. So since we have this, we're going to have that v will therefore be, take square root of both sides, we're going to have square root of kx squared over m, over root m. So what does that mean? We're going to have v, I'll be capturing the screen, this is equation 3. So v will be equal to what? Root k times root m, root x squared over root m. So this takes care of this, so that we have v will now be equal to x root k over root m. Now, bringing it to our simple harmonic motion, bringing it to the context of simple harmonic motion. You see, this x is its maximum displacement. And this maximum displacement is always constant. Why? Because it cannot move further than this unless the force has changed. So since the force is not changing, this x, we will take it as what? As a. So f is going to what? Minus ka. A standing for what? Amplitude. And that is what we have of this simple harmonic motion. It has an amplitude. The amplitude is its maximum upward or downward displacement. That is maximum, minimum, or maximum displacement about is what? About its fixed point, its equilibrium position. So it means that our equation can therefore become v equal to a root k over root m. So since they both have roots, we have v will be equal to what? A root k over m altogether. Is this the capturing? Is it? All right. So then we can therefore, so let me clean this off and then we start other mathematical derivation. So we know where all of that is coming from now. We know how we got all of those formulas. Now, what if we were now told to, so we know that because it's periodic motion, then we have periods, isn't it? We have period. And what is period? The period is the time taken for it to what? To complete what? A revolution, period. And why are we using revolution here? We said it is this guy is similar to this guy is similar to the to circular motion, the motion of the body in circular path. So that is simple harmonic motion. So what is going to be the period of that motion? What is going to be the period of that motion? Now, you recall that we said, so this will be equation 4, the equation for the velocity. This is going to be equation 4. Now, what is going to be the period of the acceleration? What did we say? We said period is the time taken to complete what? A revolution. So time per what? Time per what? Per revolution. Now, we also know that the time taken, we know that time, first, let's go from speed. You know that velocity is equal to displacement over time. Displacement over time, right? So what will time do? Time will equal to what? The displacement over what? Is velocity. Isn't it? So, but our time here is the period. So since our time is period, we are talking about what the time taken to what? To move around the entire circle, since our time is period. So since our time is period, therefore, we have that the time taken to move around the entire circle is going to be the distance is going to be the entire circle itself. So what's the distance for the entire circle? That's 2 pi r. So and our r here is actually going to be the amplitude. Why is it going to be the amplitude? The amplitude because just like the radius is not changing. Just like the radius is not changing, so also the amplitude of that motion is not changing. The amplitude at every instance is the same. So since the amplitude is the same, so we have that our equation, so this over v, as we said, x is now, since x is the circle, that's 2 pi r, that's the circumference of the circle. So we now have this. So t will therefore be equal to what? 2 pi a over v. So I hope we are understanding where this is coming from. All right. So since we also have that our velocity, now recall, yes, we can now recall that velocity is equal to a k over m, I think. Yes. So we can now say that t, therefore, is equal to 2 pi a over a root k over m. Now, you see, the idea with this YouTube channel is that I always want you, or I always enjoy you to not cram but understand where these equations are coming from, because I have, from experience, faced a lot of trouble with doing exams because of tension. I just feel uneasy and then I forget formula. So, but when I know where the formula is coming from, I go all the way to deriving from the beginning. Now, the truth is, since you're a smart student, by the time you begin to derive it, you quickly recollect. So understanding it helps you to understand, to even remember formulas. So in case you are beginning to ask yourself, what's the use of all of this? So A can cancel A. Therefore, we'll have that T, our period, is going to what? 2 pi over root K over root M. So when you are dividing by fraction, what happens? The denominator goes up. So we have T will be equal to 2 pi root M over root K. So T therefore is what? 2 pi root M over K. This is equation 5. So we can quickly do something here. We know that it's also going to have a frequency. Why? Because it's periodic motion. So the frequency here, since f is equal to inverse of time, so what do we have? Inverse of this entire thing, isn't it? So let's take the inverse of this thing. So t will be equal to what? 1 over 2 pi root m over root k, isn't it? So let's do the math of that. So that we'll have so here we'll have t will be equal to 1 over 2 pi times root m times root k. I hope you understand what I did. I just brought this one up. Whenever you're dividing by fraction, I say that. So I mean F now, F, not C. F is inverse of time. You remember inverse of period. So here we are going to have F. So that F now equals to what? 1 over 2 pi root K over M. So and that's going to be our situation for frequency. So that's going to be the formula for frequency. Now, let's quickly talk about what is this now. Now we've been talking about the actual all of these properties of the motion in circle. What if we now talk about analyze the motion of the body, its maximum horizontal displacement, since it is moving in a circular path. What we want to discuss, no, its maximum horizontal displacement is going to be the amplitude. Its maximum horizontal displacement will be the amplitude. It can never go beyond its amplitude. But its displacement is horizontal displacement at a particular instance. As in, for example, since the body is moving in a circular path like this, if it moves here, for example, if the body is around here, since it's moving in a circular path, if the body is around here, it has moved, this is amplitude, isn't it? But relative to it, to the horizontal, we have two axes, there are two axes of symmetry in this circle. So the y plane and the x plane. So in its x plane, it has moved a particular distance, x. I don't know if you got that. If the body were to be here, for example, if the body was here, now it has, by its amplitude, it has moved a particular x distance. It has been displaced away from, it has, this is what I'm trying to say, that at a particular instance of time, that body is having a horizontal displacement. A horizontal displacement. Its maximum horizontal displacement is when it comes to this horizontal. So, for example, if it comes like this and gets here, this is maximum horizontal displacement. But at every particular instance, away from that horizontal axis, it is at a particular x plane. It is on a particular x plane. Do you understand? So it's on a particular x distance, which is x here. So and it's moving by this amplitude, because the amplitude is the same as the radius. I hope you understand what I'm saying. The back and forth movement of that is still the same as its radius. It's not going past that unless the force is changed. Keep that in mind. All right. So we have x here. It's going to be the what? The x plane. So how do we analyze this? We now have this place to be our theta, for example. So let's bring out that triangle. So we have this. We have this to be our theta. We have this to be a. We have this to be x. So what is going to be x if we are looking for x? X is going to be related to what trig function. So we're going to be using our SOHCAHTOA now, right? This trig function now. What trig function relates what side relative to this angle? What side is this? This is going to be adjacent, right? And what side is this? The longest side, hypotenuse. So what trig function is that? Cos rather. Cos theta is going to be what? Adjacent x over what? Hypotenuse A. So therefore, the x, the horizontal displacement at a particular time is going to be A cos theta. So this is where this is coming from. I hope that is clear. Okay? Now, so from here, we know that so what we have is A cos theta, x equal to A cos theta when you cross multiply. Okay, so we can take our velocity. Velocity will now be equal to change in x over change in time, right? Change in displacement by time. So we have dx over dt, dx dt. So we can therefore take this with respect to t, but t is not appearing in our equation yet. So how can we make t appear? Recall that theta is equal to omega t. From where we did in simple harmonic motion, you know that omega is equal to theta over t, angular change in angle over time. So when you cross multiply, you're going to have theta equal to omega t. So that's where the equation came from. So with this we have this. So x will therefore be what? A cos omega t. So dx dt will be equal to dA cos omega t dt, isn't it? So, and how do we do this? This is what kind of function? This is going to be a function of a function, because this is one function and this is another function here. So we have let u be equal to omega t. So that our question is now x will now be equal to what? A cos u. Is that okay? So from here, dx du will be equal to what? Cos theta is equal to negative sine theta, isn't it? Good. So because of that, this will now become dx du will become minus a sine u. Then from there, since u is equal to omega t, du dt will be equal to t is to 1 degree. So when you differentiate something that is 1 degree, it becomes 1. Alright, so 1 times omega is omega. We are not differentiating omega, so omega just appears there. We are not differentiating it. That's why A is also appearing. So what do we have here? We have the x dt will now be equal to dx du times du dt. So we now have dx du. What's dx du? Dx dt will be equal to minus a. I don't think this is clear enough. Minus a dx du dx dt will equal to minus a sine u times du dt, which is omega. So what do we have? This time this becomes dx dt will be equal to minus a omega sine u. And since u is omega t, dx dt therefore becomes what? Minus a omega sine omega t. How is this clear? Is it clear? Okay. So that's that for this. That'll be it for this video. In the next video, okay, you might even decide, since this is the velocity, you might decide on your own to try the acceleration. So this velocity here, this velocity. So you might decide on your own to try on the acceleration. Okay, in fact, I'm going to give you the assignment, try the acceleration, but I'm going to do it here separately. But I want you to pause the video and try on the acceleration yourself. And how do you go? But let me quickly give you the hint. The hint is like this. The hint is this rather. Since you know that acceleration is dv dt, so you have v to be this. So v is minus a omega sine omega t. So I'm not going to work this out in full for us, but what you will get is going to be a acceleration will be equal to, when you are taking the trick for function of a function is just differentiate this, you get cos omega t, differentiate this, you get omega, then this one you are not differentiating will still be left, so we have minus a. Now we had omega here before, so let's rewrite that. I think I'm wrong. So we're going to have a will be equal to, what we are not differentiating is this. If you differentiate this, you get omega times this omega that was here before, times, if you differentiate sine u, sine theta, you get cos u, which is omega t. So our answer is going to be A equal to minus A omega squared cos omega t. And that is the answer for the acceleration of this in simple harmonic motion. So do well to subscribe to the channel if you have not already. You see here, we always make sure you understand the concept, but without cramming, without having to cram. And that's the essence of this channel. So I've discovered a lot of people are fond of cramming for cramming formulas in physics and chemistry and maths, and they feel like it works. But at the end of the day, when they are faced with very tough situations, the tension and all of that makes them to forget all of these things they've crammed. But if you understand it, nothing can shake you. You understand? So that is why you have to subscribe to this channel so that you won't miss out whenever I drop any such interesting video. And share with your friends, of course, and also like the video. God bless you. Also comment any question you have on this topic.